Hi, it's Daniel with TrustGraph, and today on Engineering Thoughts, an idea that I got from the TrustGraph co-founder Mark that I'd actually never thought about it quite this way. LLMs are slow readers. I mean, when he said that to me, I first thought, what does that mean? And then I gave it a couple minutes of thought, or not that quite even that long, and I went, oh, I get what he's meaning. That's really interesting. I'm really surprised more people haven't thought about LLMs in this way. So I thought, what a great topic for another episode of Engineering Thoughts. So what does this actually mean? Well, let's think about a traditional data science pipeline, and whether you're using regex, probably not, because that's not going to be quickly particularly fast. So let's think of a modern data science pipeline where you're processing lots of text-based documents. Um, Just a number I threw out. Let's just say you're talking about processing some sort of document in 50 milliseconds. That seems somewhat reasonable. And I think that's the important point to think about here is that when we think about traditional document processing, data processing, even for large documents, large data sets, we're typically thinking about this on the order of milliseconds. Whereas LLM latency is very, very different. I have here, just best case scenario, we're thinking about 5 seconds latency, but let's be real, that's more than best case scenario. The only reason I think that there's a perception that LLMs respond quicker than that is most of the AI services, whether it's ChatGPT or Claude or Gemini, etc., they stream the responses so that within roughly a second or so, or maybe a little bit less, you get something coming at you. But the full response often takes quite a bit longer. I know with Gemini, if you give it quite a bit of long context, it still could be 20, 30 seconds or even longer to fully complete the response. So we're looking at a huge order of magnitude difference in these time scales. So, what does that really mean? Well, let's think about if you had 1,000 documents. A traditional data science pipeline processing 1,000 documents at 50 milliseconds each, we're looking at 50 seconds. Well, that's not so bad, less than a minute. But what if we're thinking about LLMs that's 5 seconds each request? Well, it's a little bit different. We're looking at 83 minutes. That's quite a difference in time scales. So, what happens when we begin to scale up? We think about, oh, 1,000 documents. Well, how often are we going to do that? Well, if you're a large organization, a large enterprise, you may be continually ingesting that amount of information because your data is continually changing. If you're using AI to potentially evaluate logs, oh boy, that's constantly, the tap is just on full blast all the time. So, doesn't seem that unrealistic at all. Or even think about, well, a POC or a demo, you only have one or two users, but what happens when there's 1,000 concurrent users, 10,000 concurrent users? It's not just document processing, it's all the requests. If you have some sort of RAG pipeline where you're having to pull information and package it in the request, or even chat history, this is all data that's got to be packaged in these requests and sent to the LLM for processing. And you can get a monstrous backlog of data just sitting, waiting to be processed. Whereas with traditional data science pipelines, it's much more, I guess the term that we use sometimes with Pulsar is fire and forget, and on a very smaller time scale, so that in less than a minute, these jobs are already done. They've already been processed. But with an LLM, they're just sitting there waiting. And this term cache, wow, as they get thrown around a lot these days. I see the term caching get thrown around like it's this magical free thing. Oh, cache the data. It's still storage. It still requires memory to store it. and then to manage it. So this is still a compute resource that you have to provision if you're using it in cloud. If you're using your own hardware, you have to have that memory. So cache is not this free magical data storage that you can just say cache and it's taken care of. And not only that, what happens when this data that you were caching that you all of a sudden now want to do something with? So now you have, whether it's chat history, whether it's the RAG request, whether you're just trying to create an audit trail for the request, what data was used as the context, when the request was made, what model was made, used, all that sort of metadata, what was the temperature settings, et cetera. Does anybody even do that anymore? Good question. You have to manage all of this data. It's not free. It's not magical. Um, you can't just throw together, a Postgres table and say caching, and boom, magically it's all done. For POC, sure, maybe, but when you have constant ingest of data, when you have many, many concurrent users, or let's just be honest, that's a reasonable amount of concurrent users in today's world. If you're having some sort of app that's being commercialized, it's consumer or even enterprise, some of this data you're going to want to store permanently. So you have to have pipelines that can store that data temporarily, then choose what's going to be stored and how it's going to be stored. And then not only that, how are you going to be able to retrieve it when you need it the next time? So what does that lead us all to? You can probably guess where I'm going with this. This is why, data streaming backbones come into play here. Because let's think about this in an example. So, and this could be another topic for another engineering thoughts. A lot of the design I see for modern software is designed around an ideal networked topology, in that there's this assumption that transmitting between point A and point B, nothing could go wrong. Well, if you're doing that on a closed network, that might be true, but is there anything that's really a closed network anymore? Not really. Everything is using cloud at some stage or some degree of public infrastructure. And when you're using public infrastructure, public networks, you can't guarantee those connections. How many times have you been in the middle of a meeting and your internet connection drops out? Your Wi-Fi at the coffee shop drops out and comes back a minute later. Well, if you have this monstrous backlog of messages that your system is processing and somebody's connection gets broken, what happens to those messages? If you don't have a way to keep track of them, to label them, to order them and queue them, all of a sudden messages could show up out of order. Maybe the context didn't come with the message. Maybe there was one of the steps in the process, performed a RAG request, pulled that context in. That part didn't get sent, but maybe the LLM request got sent. So the LLM request gets sent without the context, or even gets sent without the chat history. And that's why technologies like Apache Pulsar are so important, because it gives us a distributed way. Well, actually, it's distributed and centralized at the same time. But we talked about that last episode. And if you're interested, we can continue to talk about this. But it gives us that ability to queue all these messages, to store them, choose what to store, not to store. Because remember, data streaming is not just about moving data, it's also about choosing what to store and where to store it. And because of that infrastructure, we can manage these huge workloads. We can mitigate the issue that LLMs are slow leaders, because as we accumulate that backlog, we have a system that's resilient and reliable enough to manage all that data, because that's what it's designed to do. It's storing all that data in an ordered queue with acknowledgments and non acknowledgments to know when data was received and when it wasn't received. This is really one of the key features that AI architectures are missing, but not in TrustGraph.